Well, welcome back. We are looking at statistical tests that we can apply to the data that we collect to evaluate its strength as evidence to support our argument. And in this case, we're looking at what happens if our dependent variable is actually a continuous variable. So we don't do a chi-squared test. In this case, we do a student t-test. It was developed by the chief brewer at the Guinness Brewery as a way of measuring. Imagine you had two farmers that are growing some crops that you might need for brewing Guinness. One of them, looks like there's more of a yield there than the other one. How do you actually know? We're going to take a sample of the heads of the barley or whatever, and we're going to weigh how many grams of seed we get from each of those samples. But it's not, it's not every single barley head in the field. We're just taking a few samples. How do we know whether the difference in the average weight of the barley heads between those two fields is actually enough to be worthwhile paying one farmer more than another? So a t-test is used to decide whether the difference in means, the difference in average between two sets of data is actually significant, or if it's just all due to random chance. So here we have our fish again in the fish tank, and we looked at the color of light last time, and we're looking at the color of light this time, but we're looking at a continuous variable, the number of times on average they open their gill every minute. Okay, this time I only observed them for a minute, so it's kind of a whole number there, but it is a continuous variable. If I observe them for 5 minutes divided by 5, then you could have a decimal place in here. So it's a continuous variable, and we can see down the bottom here we've got our means. One mean is 30, the other mean is 27, but I've made 32 observations of fish. The other thing worth saying here is that I've actually put this column here as fish ID, right? So presumably, of course, all of this data is fake, so please don't, put any weight in the conclusion I'm doing. I've faked the data for the purpose of the exercise. But let's say that fish 1 happens to be my favorite fish, and so I can identify all 30 of my fish. And so these observations are the fish number 1 in white light, red light, and blue light, and this is fish number 2. And so it's the same fish in different conditions, and that'll become important a little bit later on. Okay, so a t-test. How do we do a t-test? Well, you might have looked up a whole lot of things. You get a value, and then you look at a table and you decide whether it's above or below that threshold. No, it's all done for you like the chi-squared would be. It's going to return, the formula here is going to return the probability value. It's calculated the value, it's looked up the kind of table, and it's returning us what's the probability that the null hypothesis is correct. Okay, so we go t.test, we go equals t.test in Excel, and then I want to tell it the first array, and then I want to tell it the second array. And so what I'm doing here is I'm comparing white light with red light. The next thing it wants me to know is, am I a one-tailed or a two-tailed test? Well, I could do a one-tailed test here, and I'm only testing whether the 30.1 is in fact higher than the 27. But look, if you're not really sure, just do the two tails. That means that you're agnostic as to whether one average is higher than the other average. So let's kind of put a two-tailed there. Now, the last one here is whether they're paired. And in this case, they are, because the value for fish number 1 of 30 in white and fish number 1 for 26 in red is the same fish. And so we've taken the same subject. So any variation between the white and the red is not because they're different. If they were different fish, I'd do an unpaired. If like I had a group of fish that had red light and a group of similar-ish fish that I had in white light, then there will be some variation between those just because they're different populations of fish. But if it's the same population of fish, and I know that that's Freddy fish is number 1, and that's Freddy fish in the white and Freddy fish in the red, then I'm going to do a paired. So in this case, I'm going to choose a paired. If you're not sure, if they're two different samples, like you took barley from one field and barley from another field, there would be unpaired samples. If you, grew some barley and changed the conditions and then measured the same bit of barley again, that could be a paired test, like what I'm doing with the fish. Okay, so this is my t-test, and this is, I'm testing the red light against my control. And what I've got is a very low p-value. So that means the probability that there's no difference, the null hypothesis, in those means is actually quite low. It's smaller than 0.05. It's actually 0.001, just a little bit above 0.001. So it's kind of at that really sort of threshold that we're reasonably confident. Let's do a t-test of blue. And so we're going to go equals t.test. In this case, we want white, again, as my control variable. I'm looking at the difference between the white and the red. They are looking pretty similar means there. Whoops. I'm going to do a two-tailed, and I'm going to say that it's a paired t-test here as well. Now I can see that my t-test value comparing blue to white is actually quite high, so I'm going to accept the null hypothesis for blue light, but I would reject the null hypothesis for the red light. In other words, it seems to be that there is some statistically significant difference in the fish because of the color of light. Or maybe it's not. This is when we need to, not be statisticians and use statistics as a tool to help us decide the value of the evidence. But we've also got to be scientists. Okay, so what are the other confounding factors that might mean that changing the color of the light there's more going on than just changing the color of the light? Now, you might think of a whole lot of things like temperature and whatever, but if you think about it, it could actually be intensity of light. I mean, who's to say that the blue LEDs are as bright as the white LEDs? White is actually the red, green, and blue LEDs all on together, and blue is just the blue ones, right? But also, it's really how a fish would perceive the brightness. Like, if their behavior is going to be affected by it, they have to perceive that brightness. So the more important question is, does the blue light look, or the red light look, difference in brightness to the fish? Because, I don't know, maybe this species of fish are colorblind and they don't actually have any color sensors. We dissect their eye and we look at the anatomy of their eye and we find they've only got rods, in which case they're only monochrome, sensitive to shades of grey. Then maybe it is actually all to do with that. So that's where we've got to be careful. And that's where we need to talk about the tests to go between, there's a correlation, is it causation? You need to have a pretty good correlation to begin with, but even then you need to be thinking about what are all those other possible confounding factors that could mean that I'm seeing a change in their behaviour. I think it's because I've put them in red light and that changes their behaviour. But am I actually measuring what I think I'm measuring? Am I measuring the effect of the colour of the light, or am I measuring the effect of the intensity of the light? I'm measuring the effect of, what the other confounding factors might be. And that is the question of validity. So when you're doing science extension, validity is, are you measuring what you think you're measuring? That's the simplest way of thinking that question. That's why we control all the other variables that we can, so that we're pretty sure that when we see a difference in the dependent variable, it's because of the independent variable. But you know what? There's always potentially some confounding factors that we haven't thought of. So that's how to do a t-test. It's really, really simple. Most scientists, just use a spreadsheet or some other computer tool to calculate that for them. What they need to know is, what is that value and what does it actually mean? What are the situations in which it would be reasonably valid to make those conclusions? How strong is this evidence to support the claim that I'm trying to make that the colour of light might actually affect the behaviour of our fish?